today we're going to talk about section 1.3, which is intersections of a pair of lines. All right, so if there are two lines in a plane, there are three possibilities of how they can interact. If they're parallel, like this, then there are no points in common. If they cross, there's 1 point in common. And the other possibility is that they're actually the exact same line. So that's of course not exactly the same because I can't do that perfectly, but they're the same exact line. And that means all points in common. So those are the three ways these things can happen. The way that's most interesting for us is this 1 point in common way. That's usually what's going to happen when you've got two equations and you're trying for them to both simultaneously be true, is that there's probably just 1 point in common. So we want to know how to find that point. Right? Now, I mean, it's right there, right? But I mean, when we have the algebraic formulas for these lines, how do we use the algebraic formulas to find that point that they share in common? Okay. So how to find a common point. Okay, let's do an example, of course. If we have y equals 2x minus 3 and y equals x plus 1. So those are two lines. We can graph them here if we want. Let's make this the origin. 2x minus 3 will have this point and then this point. Maybe I can get some sort of straight edge to make this even better. So that's y equals 2x minus 3. And then x plus 1 will have the point 0, 1, and then 1, 2. Right? It'll be this line here, connecting those 2 points as so. So this is y equals x plus 1. So what we're looking for is we're looking to find where that point is, where those two cross. That's what we're looking to do. And it's not a very difficult procedure to figure this out. What we do is we have solved for y for this 1 point and also for y for the other point, so we set those equal to each other. So we say now that 2x minus 3 is equal to x plus 1. Since they're both equal to y, I can set them to each other. All right, when I do that, now I need to use algebra to solve this. I'm going to add 3 to both sides to get 2x is equal to x plus 4. Then I'm going to subtract x from both sides to get x is equal to 4. So it looks like they join together when x is equal to 4. So this is the x coordinate of the intersection. Now to find the y coordinate of the intersection, then I go back up to either of my two equations and plug in that x. And either one will give me the right y for the intersection. So let's say y is equal to x plus 1. So y is equal to 4 plus 1. Which is 5. So y is equal to 5. So the solution to both of these equations is x equals 4, y equals 5. And looking at our graph, we'd have 1, 2, 3, 4, 1, 2, 3, 4, 5 course, this picture isn't perfect, right, but it's in the right vicinity. All right, so we found the intersection point. You might write it as just 4, 5 is the intersection point. Or you might see it written like that. Okay. Any questions for me about this example here? Is this good? Okay. Now there are other ways to solve this. Let me show a different way of solving it. Maybe you're more familiar with this other way. Okay. We have, well, no, I guess that's not going to work here. I'll show a different example. Yeah, this example will be good for highlighting the other way. We want to find the point of intersection for x plus 2y is equal to 6 and 5x plus 2y is equal to 18. Now in this example, we don't have y equals 1, y equals the other. And so we can't just set them equal to each other and solve for x. So we're going to have a slightly different method. Now, you could first solve both of those equations for y by doing what we've done in the first lesson or two, right? You could do that, which is fine. We're going to try some other method, a method sometimes called substitution. Let's take a look at this first equation here. X plus 2y equals 6. If I subtract 2y from both sides of this equation, I will get x equals 6 minus 2y. X equals 6 minus 2y. So that means the relationship of this first equation is that whatever y is, you take 6 minus 2y, you get x. So what I'm going to do is I'm going to take this and plug it in the other equation. Instead of having 5x plus 2y in the other equation, I'm going to put in 6 minus 2y instead of x. Okay? So let's show how that works. So instead of 5 times x, it's whatever x is equal to. And there we have 5 times 6 minus 2y, and then plus 2y equals 18. Now we need to use the distributive property in order to solve this, right? We have to multiply this 5 through both of those items in the parentheses. So 5 times 6 is 30. 5 times negative 2 is negative 10, so it's 30 minus 10y plus 2y is equal to 18. All right, so now we continue our journey here. So this is 30 minus 8y is equal to 18. Now if I subtract, I'm going to add 8y to both sides, just because I prefer not to work with negative numbers when I don't have to. And now I'll subtract 18 from both sides. I get 12 is equal to 8y. Okay. Now I'm almost done finding y. I now know that y is equal to 12 divided by 8, which is the same thing as 3 divided by 2, when we cancel out the 4's. So y is 1.5. And now, to figure out what x is, I go back to this situation there. So now x will be 6 minus 2 times 1.5, or 2 times 3/2. See, I've plugged in the y value that I found back into the other equation to figure out what x needs to be. Okay, by doing that, I get x equals 6 minus 3, so x is equal to 3. So the point of intersection is 3 3/2. Any questions about that example? Notice I didn't even graph, right? If I trust the algebra enough, I don't need to graph, right? But, if you have who has a graphing calculator that they use when they do their homework? Do you guys have graphing calculators? Probably a fair percentage of you do, right? So one way to check your answer is to graph both of these. Now, the problem with graphing both of these is these aren't in y equals format. So you'd have to solve for that anyway. And you might decide that that's too much trouble. I'd rather just trust my algebra skills, right? But there's ways to check all of these things. Well, another way to check is you just plug this into both equations and make sure it works, right? We know it works with the first equation because that's how I found the pair. But if you plug in this value into this equation here, you'll see that it works. So 5 times 3 is 15. 2 times 3/2 is 3. 15 plus 3 is 18. So it works. It works. All right. Another example. So we'll do more of a word problem type example. Are you guys familiar with the concept of supply and demand from economics, right? Supply is the thoughts of the producers of a good. If I know I can sell something for $10, I might make 5 of them. But if I know I can sell it for $20, I might make more of them because I can make more money, right? Now, demand works the other way. If something is available for $5, I might buy 10 of them. But if the price increases to, $10, I might buy many fewer of them, right? So this is the classical economic theory of price discovery. So let's have a supply curve. And that's going to be P is equal to 0.0002 Q plus 2, where P is in dollars and Q is a quantity. So the supply curve, that's what the business is thinking of. If the price is higher, I want to make more of it, right? If the price goes up, Q goes up in that equation too. Now the demand curve, that's what people would pay, and that's going to have a negative slope. So it's negative 0.0005 Q plus 5.5. Okay. So that's that's how many things people will buy if the price is set at a certain point, right? So the price is set, and then you solve for the quantity, or you decide the quantity you want to make and you see the price that you'd be willing to pay. Now those are two lines, and where they intersect is called in economics the equilibrium price. And this is according to economic theory, this is the price at which the market clears and the goods are sold and produced at. So we want to find the market price here. We want to solve these two together. Now, who likes decimals? Does anyone like decimals? No. I don't like decimals either. So let's nuke the decimals. Does anyone know how we nuke the decimals here? The first one is, let's see, that's a tenth, hundredth, thousand. That's 2 10,000ths in the first one. And the second one has 5 10,000ths. I don't like dealing with 10,000ths. I like dealing with ones. Right? So I'm going to multiply both of these equations by 10,000, and then I will eliminate the decimals. So 10,000 times the supply curve, I'll write it here shortly, is going to be 10,000 P is equal to 2Q plus 20,000. So that's the new supply curve. And then the new demand curve is going to be 10,000 times this curve here. Now, one thing to note, you don't have to multiply both equations by the same number. It just so happens that both of these have 10,000ths as the decimal, right? You're not changing that equation at all by multiplying both sides by the same number. It doesn't actually change the values that it's true for. It only changes the values that we're looking at in order to manipulate, and we're changing them into numbers that we're more familiar with dealing with than decimals. So this is going to be 10,000 P is equal to negative 5Q plus 55,000. Because when you multiply 5.5 times 10,000, you get 55,000. Okay, now we want to solve both of these equations simultaneously, right? That first equation is a line, if Q is the x-axis and P is the y-axis, that's an increasing line. The second one's a decreasing line, so they have to intersect somewhere. And we want to find out where that is. So the way that we figure out where that is we use the techniques from before. Now note, this one's actually kind of very nice for us. On the left-hand side of one, we have 10,000 P. And on the left-hand side of the other, we have 10,000 P. Those are exactly the same thing. So this is more akin to the first example we did where we had y equals and y equals. We can now set the other halves equal to each other and solve for Q because they both have 10,000 P. So that means I can write 2Q plus 20,000 is equal to negative 5Q plus 55,000. Okay. Since they're both equal to 10,000 P, I'm kind of doing a substitution right now. And just setting the right-hand sides equal to each other because the left-hand sides are equal to each other. Now, this is going to be a lot easier to solve, right? I can subtract 20,000 from both sides. And I get 2Q is equal to negative 5Q plus 35,000. Now I add 5Q to both sides. And I get 7Q is equal to 35,000. So that means that Q is equal to 5,000, right? Because 7 times 5 is 35. So the quantity produced is going to be 5,000. Now we want to find the price at which that is going to happen for. So now we need to find P. P is equal to, let's use the supply curve, 0.0002 times 5,000 plus 2. Okay, so 2 10,000ths, okay, this is 2 10,000ths. That's what 0.0002 means. Okay, so then, let's see. That is exactly 1 plus 2. Okay. Now, I know I'm doing a lot of algebraic tomfoolery here with multiplying by large numbers or changing a decimal into a fraction, right? You may not have the facility with that, but right, you've also got a calculator you can use too, right? So you can use a calculator. That's not a problem for me. But I want to show you sometimes that not using a calculator, you can still come up with pretty clean and easy numbers if you work carefully. So now the PQ solution is 5,000. So we will produce 5,000 of this item if it sells for $3, and that's a price that where the buyers and sellers meet together and agree that this is what we want to do. Questions about this one? Okay, let me write down the in-class work, which I know you won't have time to finish today because we've burned a lot of time waiting to get this display thing working. But I'm going to write those down anyway, and I'll also write down the homework. So in class, let's do, this is section 1.3, 1, 3, 7, 11, and 13. And then the homework is going to be 2 through 12 even, 14, and 18 through 24 even. Why I wrote it like that, I will never know. I guess I could have said 2 through 14 even, right? The product of a depraved mind. Okay, so I'm going to stop the video now for our friends who couldn't be here.